Hi all, welcome to the NPTEL online certification course, and this is the online teaching assistantship program for biophotonics course. And this is our sixth module. Let us wait for some time for other people to join also, and we can start the discussion. I'll introduce myself. I am Jijit, and a disciplinary scholar of chemistry and biotechnology from Indian Institute of Technology, Madras, and I am mainly working in single molecules 14 biophysics using optical tubes. Let us start. In this video, actually, we will be solving the model problems of for lecture 6 or the week 6 part. And along are we are going through this video part or that problem solving skill. Actually, we will see different aspects and we'll give a proper explanation for the same. So let us start. And in that in this week 6 lectures, actually we told or we taught about mainly regarding the imaging part. So now actually I will give a brief introduction regarding imaging and some normal microscopes and other details, and we'll start solving the questions. Okay, now let us start with the brief introduction about the imaging. So let us start. So I'm going to share the entire screen now. Hopefully this is visible for you. So let us start with the basic concept of image. And imaging is a process of forming an image. So what is actually image? Image is a one-to-one recreation of a particular object. And so if you are using our normal thing, in a normal thing we are using our eyes to see. So usually we will use our eyes to perspect the vision, and the image is the one which we are seeing, that this is a replica of an object which will give a perspective of the object in the form of a vision. Okay, so to get an image, so what you want, we want an object. Let it be one leaf is my object. Now what's a leaf? That's a leaf here. So actually I want a replica of this object. Let it be big or small. So you can see if this is an object and this is an image. So what makes it is an image? I can say that there is always a one-to-one correspondence from object side to image side. If I see, look at this portion of object, there will be similar portion on this object. So there is a portion in this object, there is a another portion this here. So there will be all spatial definition, there will be a similar point in the image also, then only it is making a proper imaging. So if this is a my object and this is an image, and this is some imaging system, so you can map from here to here, here one to one correspondence, here, 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 somewhere here, here. So in this point actually what we are seeing actually what is giving image in the form of vision. So it completely depends on the light. So how this is becoming a good image? So we know that to see an object actually I want light. How we are seeing an object? We are seeing an object by, so if I have an object, let this apple be my object. So there is an object, and here I am seeing using my eyes. My eye I am seeing here. So there should be some light source. It be sun or something. There should be a light source, and from the light source, what happens? Light is coming, and usually that is a white light. Now I'm just putting it this like object, and light is hitting here, and the corresponding to that one, lights are actually getting reflected from here, and it is reaching my eye, and light is reflected from here, reaching my eye, and inside the eye actually there is some imaging is happening. And how it is becoming an imaging, and now you can see that we are going to see, and a prop. So we can see that the light from the sun will reach and hit on an object, and it will get reflected, and it can get reflected at any direction, depends on the sunlight. So you can see that from this point, this light also get reflected here, also light will be reflected in different directions, depends on the rays coming there. So here also there will be light, it's reflecting this side, reflecting this side, reflecting this side. So if there is a illuminating body, it can be illuminated by itself, or it can be a reflection from some another light source. So there will be light rays which is traveling at a different points. So what actually we want, if we want a proper imaging, the light ray which is originating from one point should reach at the particular point of the image. If the light ray, all the light rays which is emanating from one point should reach at the one point in that image system also, then only we can see it is a proper image. So So this is my object, and I want the image of the system. So what should be required? I want, so I know that from this point actually lot of lights are emitting, and this light should reach at the corresponding point here, and it will become a proper imaging if all the lights which is emanating from that point is actually reaching the, if all the points which is actually emanating from this point is making another point here, that would be a good image. Similar way, all the points which is emanating from this can be this here, 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 and it should reach at that point. So then only it is becoming a proper imaging system. Okay, so it will make all the points from an object is focusing or just reaching at the same particular point in that image, then it is called a proper imaging system. So it will give a one-to-one correspondence of that particular object, and it will be a good image. So what happens if that all rays are not reaching there? Still it can form an image. If this very small portion of one object is only reaching here, it can make an object image, but the image clarity or the quality of the image will be much less. You will see a diminished image if it's like half of the portion of the light is not reaching here. Then what happens? Your image will be less intense, or it will be like diminished. And there can be another problem also. Corresponding to this light only should reach here. If this light is actually focusing here, what happened? Here you will get a green point, and that will make your image distorted, something like that way. So every point will should map another point rather than, and there should not be any. So corresponding to one point, there should be one point. Corresponding to another point, there should be another point. And if all the lights coming from one point is reaching at the same point, then we will get a sharp image. And if different portion of an object is coming at a same point, then you are going to get a blurry image or something, because that will not be a proper image or something. Okay, now we want to know what will be a thing which can be used as an image system. So the simple answer is actually a lens. A lens can be used as a good imaging system. So, so we can see how a lens is actually acting as a good imaging system. So the lens has a property that if the all, it can, just consider, I'm not saying more complex definition of the lens. Now I'm saying about only about a thin lens. The thing is that all the rays which is coming at a particular angle will focus at a point on a focal plane of the lens. If this is the focal plane of the lens, just I'm saying, defining the focal plane. If all the rays are coming in a parallel manner to a convex lens, convex lens is a converging lens which will converge the whole parallel rays to a single point called the focus. And this distance is called the focal distance f, and a plane which is carrying the focus is called a focal plane. Why this is important? Because all the rays which is passing on a lens is not focused on the particular principal focus. It is actually the focal plane that is giving a big matter. So just see that all lines, all the rays which is parallel and passing to the particular angle will actually focus at one point on the focal plane. Focus here, the rays which is coming parallel will focus here. It's like that. So what is actually good thing about this one? So if there is an object here, if I have an object, there's a clown mask or something, and there's a lens here. What can happen? The point, the light which is coming. So I can consider almost all parallel rays here, and that will reach to network to pass through the focus. I'll make it more clear. That's a lens. I'm not going to tell all the properties of the lens. The light which will pass through here will go, and this is the focus. Pass through the focus. The red light which is actually passing through here go and deviate. Correspondingly, I can get a image here. So just I am considering that actually two rays are coming here, which is coming from the different path, but actually eventually it is reached at the same point and is got focused. So corresponding to this point, there is a point here. So At that point, there will be the image of that particular point. So similar way, now if that is an object, this is produce an image, and a lens can actually do a imaging of a system. And if this image is done by a system, and if you put a plane or a screen here, you can see the image of the system on the screen. And this kind of an image where you can put the image on a screen is called actually a real image. An image which can be actually put it on a screen is called a real image. Now see that if the object is very near to that lens, the object is very near to the lens. Go here. This is the focus distance. Go like this. Just like coming from here. Go like this way. So actually, if you see from this side, you see from this side, what we will see, we will think that the light is actually coming from somewhere here. Actually, light is not coming from the light is coming from here only. But from the view from the eye, actually, we will think that light is coming from this much big objective. So, but you cannot put this. You can see it as a big image of your objective, but you cannot put it on a plane or something. So that kind of image is actually called a virtual image. Okay, these are actually I'm saying about the basic things of the imaging. Now we can solve our questions. Let's start our questions. Sorry for the technical issues. Okay, let's start solving our problems. Now we will see our first problem. Along with each problems, actually, we will see how to what are the concept which is told inside the problem also, and we can solve. Major similarities between a simple and a compound microscope. So we can see now we can see what is a simple microscope and what is a common microscope. Okay, now let's see what is a simple microscope and what is a common microscope. Now, so as I told in the first, lens with a virtual image, actually a lens in the form of a virtual imaging, that's actually called a simple microscope. So if the lens, convex lens, which we kept it very near in the sense that in between your focal point and the, if optic center of the lens, what will happen, the light ray which is coming, uh, pass through the focus, and light which is coming to the optic center will pass under it. So under it. So what is the effect? You will see light is coming from very far away at the point of intersection. We will see that, feel that there is a big object is there. So that is the image, and this arrangement is called a simple microscope. In this model, the lens is using as a imaging, but the image is a virtual image. So this is a simple microscope, consists only one lens, and it will make a magnified image or the virtual image of a object. It's a magnified virtual image of an object. 1 minute. So so this is, yeah, in a simple microscope it will make a virtual image. Yeah, in a simple microscope it will make a magnified virtual image of the objective. So so now we want to see how a compound microscope works. Now we see that in this particular configuration, the lens acting as a magnifying glass and it will make a virtual image. Now we can see how it can make a compound microscope. In the compound microscope, what you will have, there will be one lens. In the lens, our object will be between f and 2f. So what it will make, after passing from the lens, pass through the focus, and the light passing through the optic center, and it coincide somewhere here. But in this position, what we will get? We will get an image. This is the objective of the, this lens is called the objective of a compound microscope. So there will be a specimen and the objective lens will make a real image. You can see this is a, lights are actually meeting here. So if you put a screen somewhere here, actually it will make a real image of that particular object. So it will make a real image here. But what we will do, we will put another lens here such that this lens, the object will be between C and focus. So what happens then? If you consider that light is coming here, it will pass through the focus of the lens, and that light which is passed through the optic center will go like this way. And if you extrapolate this one, we will get a very big virtual image of this one. So this is the size of the object, and this is the size of the virtual image which we are seeing. So by using two lenses, actually you made a very big magnified image of a specimen, and this lens is called eyepiece, because from here actually we will see through our eyes. So we call this as eyepiece. And this is the principle of a compound microscope. Now said this is the simple microscope and this is the compound microscope. So what is the familiarity in this one? Simple microscope uses a single lens, but compound microscope is using actually two lenses, and this two lens can be actually a set of two lenses, but altogether it is acting as a two lenses, which is one objective, one is eyepiece. Okay, so now we can see what is the answer for that questions. The similarities between simple and compound both uses concave lens. Actually, they are not at all using concave lens, so it is not. Both uses convex lens. So that is actually correct. They are using convex lens. Both use planar plane mirror. None of them is using plane mirror. So that's wrong. So it's also becoming wrong. So correct answer is B. Okay. Now let's move to the second question. Wave that is used in diagnostic ultrasound is now. Now we can see electromagnetic waves, transverse waves, longitudinal waves, none of them. So now we can see what will be the most appropriate answer. So these are like optional questions coming with options. So the thing which matters is actually the most appropriate answer. So let us see here which one is actually most appropriate. So now we will see. So electromagnetic waves. What is electromagnetic waves? Electromagnetic waves are the waves which is coming because of the oscillation of electric field and magnetic field. So now see what is consisting in an electromagnetic spectrum. So there's a big entire spectrum which is consist of electromagnetic waves, which is actually if you see in the increasing order of the frequency, you will have a radio waves, then microwaves, then infrared, then coming visible. This is the only electromagnetic waves which we can perceive in the form of light. Okay, since red it will come violet. So it will be like VG or in the reverse order. After violet, there will be ultraviolet, then X rays, then gamma rays. Like this way it will come. Okay, so and the electromagnetic waves are actually transverse wave. What is meant by a transverse wave? If the if the oscillation of the if wave is moving in this direction and the oscillation of the particle is happening in the perpendicular direction, then this is called a transverse wave. So in the case of electromagnetic wave, there will be a component of electric field and there will be a component of magnetic field which is perpendicular to this one, and both will be perpendicular to the direction of propagation of the wave. So electromagnetic waves are actually transverse wave. EM waves are transverse in nature. Okay, so these are electromagnetic waves thing. And what is actually longitudinal waves? So longitudinal waves is the wave in which if the wave is propagating in this direction, particle oscillates also in the same direction. The example of that longitudinal wave is a sound wave, so which is actually a pressure wave. So for example, you are hearing some voices from a speaker. You are hearing a voice from a loudspeaker. So what happens? The loudspeaker diaphragm is actually vibrating this direction, and that is actually making a high pressure area and a low pressure area. Again, high pressure area and a low pressure area. Like that way, this is moves and reaching our ear, and these things are actually vibrating the tympanum inside our ear, and we are having the notion of our sound. Okay, so these are like longitudinal waves. And what is actually using in this? Now let's go to the questions. What wave is used in diagnostic ultrasound is? So actually there is a hint in the question itself. What is mean by ultrasound or ultrasonic wave? So our human perspective, you can see here. So everything we are seeing the nature in terms of our perspective. So we are seeing electromagnetic waves. How we are seeing electromagnetic waves? There's a big and electromagnetic spectrum is available, but which we can get or which we can interact only in the form of visual effect is only the light, and the light have a small span of 400 nanometer to 700 nanometer wavelength region. Only that much electromagnetic waves our eye can detect it, and that is actually our window of visualization. So beyond that one wavelength also, or below that wavelength also, we cannot detect. Our eyes cannot detect it. For example, if you are increasing the frequency after violet, you cannot see. Till violet only you can see 400 nanometer wavelength you can see. Beyond that actually you cannot see. The wavelength decreases, you cannot see it as light, and that portion actually see. That's actually beyond violet, which you, it's actually beyond our detection level, and that is actually called ultraviolet. So ultra is something term which is actually called, it's like above, and this is like this is the above the violet, which above of what, above our human detection level. So that is actually called ultraviolet. Similarly in the other side, you have read here, So we have the red here, and below the red also we cannot see. That's also, that's actually below our detection level, and that is actually called the infrared. So infra is a word which we use actually show below our detection level. Ultra is called above our detection level. That's for our light or ultraviolet waves. So that's the thing came like ultraviolet as well as infrared. So above violet it is ultraviolet, below red it is infrared. Similar way, if there is a sound wave is happening, here also there is our audibility range. Beyond the particular frequency we cannot hear, and below some particular frequency also we cannot hear. So that range is actually coming between 20 hertz to 20 kilohertz frequency. This is the our human audibility range. Above 20 kilohertz, we will call the something like which before we told. It is like ultra, and it is sound. So it's like ultrasonic. So it's like ultrasonic means is sonic means something related to sound, and ultrasonic means it is beyond. Beyond what? Beyond our audibility range. So that is called the ultrasonic or ultrasound. And below this one also what is called? This is called infrasonic or sound. You can say. So infrasonic waves are waves which is actually below 20 hertz. We cannot detect. And ultrasonic is the wave which is actually beyond 20 kilohertz. That also we cannot detect. But there are existing sound waves which is actually at that order. And this will be actually useful for different purpose like ultrasonic imaging. You may have heard about ultrasonography of a fetus in the womb. So you can get actually these things are actually these are sound waves only, so these are not harmful waves. So it will directly go if you have a ultrasonic probe and you can scan above your mother's uh, body. Actually you can get a reflection from the kid inside its uterus. So these are actually well accepted ultrasonic imaging technique. So you can use ultrasonic imaging to see the child inside the uterus. And this can another thing also, the same ultrasonic waves which have a frequency beyond 20 kilohertz can be used to diagnose things, as well as it can be used to treat like kidney stones and other kind of thing, gallbladder stones. We can actually use ultrasonic waves to crush, or you can put it in a resonance mode, and the stones are getting crushed by themselves because of this frequency, and we can use as a treatment also. So now we have the answer of this question. Ultramagnetic waves is not ultrasound waves. Ultramagnetic wave is a transverse wave. Ultrasound is not transverse. Ultrasound longitudinal wave. So it's a longitudinal wave, and it's a sound wave, and it's ultrasonic wave. Okay. So evanescent wave coupling can be used in. Now see what is actually a evanescent wave. So evanescent waves are actually generated when there is a interface is there, and there is like a some light matter interaction is happening at the boundary, and in the boundary like there's some reflection is happening. There will be some small field very near to that interface also, which is actually decaying exponentially. And these things are actually very useful in the case of actually when there is a boundaries coming here. And now we can say that to prepare waveguide sensor of couplets. Waveguide sensor, actually in the waveguide actually you can actually see there will be when the signal is passing through the waveguide, actually there will be, even though we say that there is no, there's 100% reflection also, but there will be a small evanescent field will be coming near the interface, and you can actually detect it at the other side. So this can be used. Dielectric microsphere resonators. Dielectric microsphere resonators are small microspheres actually used in like photonic crystals and some laser actions and other things. So these are actually when it is actually interacted with the lights, actually there will be Vanson wave created inside this one, and these things will be confined inside very sharply such that it will undergo very high resonance, and the Q factor of the resonance will be very high. So dielectric microsphere resonators is also using Vanson wave. Powering devices wirelessly, so that also we can actually use events and waves such that there will be a interface near, and if you put some detector which can actually draw the power, this field actually you can use that powering devices with wirelessly also when it's a field. So the answer will be all of them. Now example of an endogenous fluorophore present in human cells. So this is a direct question. This is already discussed much times here. So example of the endogenous fluorophore present in our human cell is that NAPDH, which is a good electron donor in different our molecular processes. So the- this question is actually a direct question. The answer is B. Microscope that exploiting the properties of evanescent waves to generate high resolution image. Let us see. And the options given here are OCT, confocal microscope, SNOM, and SEM. Let's have a 5-minute break and we'll start. So let's continue our discussion. So we have to check which exploiting the fact properties as advanced and way to generate high resolution image. So first one is a OCT, which is actually called optical coherence tomography. So let's see what is optical coherent tomography. So in an optical coherent tomography, you will have a broadband source, and there is a detector. And the broadband source will be coupled to a microscope. Detector is also coupled to a microscope. Sorry, optical fiber. And this is a coupler. And here there will be a opening and there is a mirror. And here is your sample. And usually there will be optical fiber, and from here actually the light is coming. And let it be your tissue having different layer. So what happens at a different position, the light will come, reflect and come back. This will come back. From here also it will come back, and here also it will come back. What will happen here? There will be length which we can adjust. So this mirror is actually the movable mirror. By moving the mirror, actually what you can do, moving the mirror, the path of the light is actually changing here. This is actually we are changing path, we are changing by ourselves. But when the path length is actually becoming the path length of this particular layer, then what happens, that the light which is coming from this fiber strand as well as this fiber strand actually will be in coherent, and you will get a strong interference pattern at this position at the detector. So strong interference pattern at this detector, and with that actually you can do by adjusting the, by moving the mirror, you can actually get the imaging at the different layer inside your tissue. So this is the method in optical coherence tomography. And here you can see there nobody is using actually Vannessen wave. Vannessen wave will be created somehow when there is some interaction with the light and matter is happening, and at the near the interface, and where it is like there is no physically wave is present, you can see the presence of a decaying field, and that's actually evanescent field, and you can see that there is no evanescent field is generated in OCT. So the first option will be wrong. Now what is the case of a confocal microscope? Now what is happening in a confocal microscope? In the case of a confocal microscope, there will be a light source, and let it be some laser beam or something, and it will make a the beam which is coming, and it will become a focused beam. And at this focal spot, there will be some confocal pinholes are kept to pass through the pinhole, and there will be another objective or something which is kept here, and it will pass through the specimen. And after the specimen, what happens that image will come back, and actually we will keep one dichroic mirror or something such that it will. So what we will do here, after the reflection or fluorescence, the light will come back. There will be light which is coming from the focus spot as well as the non-focus spot. So the light which is coming here, and using this some dichroic mirror, it will be actually focused here, and there will be another pinhole also. The thing is that this unfocused light will actually masked by the pinhole. So only the light which is at the focus spot will come here, and we will use it for detecting. So what happens is it will remove all the unfocused part and actually give only the focused one. So it will actually increase the definition of your image. So this also not using any evanescent wave. So this can also be, this also cannot be a right answer. Now we will see what is sum. So I think, yeah, now we can see that what will be the answer here. Now sum is nothing but a scanning electron microscope, which actually uses a, there will be a electron gun which is using different methods to produce a electron beam. There will be some electron accelerating thing which will pass this accelerating electron beam, and it will also use focused electron beam, and it will pass it on a specimen. And the specimen actually using this electric field and magnetic field, you can actually scan the beam through the specimen, and the backscattered or secondary electrons actually we can detect with the various detector, and you can get an image. And this is called a scanning electron microscope. In this one also, what happens, you can see there is no usage of a evanescent field. Now the answer is only S norm. And what is S norm? S norm stands for scanning near field optical microscope. So in this one, what is happening? In this one, there is a near field is the place where actually you are using a light source and very near to that field. So it is actually, near field is the place where your distance is actually lower than the wavelength of the light. So this distance is less than lambda, and if you use a fluorophore or something, there will be near field interaction to that one, and it will actually give high resolution imaging because of that near field waves. So because of near field waves, actually this is a Vanson kind of field. It's actually to generate, and because of that one, actually it will give a high resolution image, because this is using the near field waves. So the answer is actually scanning near field optical microscope. This is also a direct question. Actually, GFP, a green fluorescent protein, is actually isolated from Aquaria victoria, which is actually a jellyfish kind of organism. So the answer is actually. Now the question is, OCT images obtained by measuring intensity of reflected light, intensity of absorbing light, intensity and transmitted light, both B and C. Now we already see that how an OCT works. This is the OCT working principle. So here we can see that what actually they are measuring. There are two lobes. This is the source. This is the detector. So from here actually light is going. There will be a fiber coupler here. From here, this actually is split into two. One is going here and another is going here. It is going here and after that is coming back. This is going here and the reflected light is actually coming back. When the reflected light in the specimen arm and the reference arm, the path length are equal, and there will be a, that means they are in phase, and because of it, they are in phase, there is a coherence happening, and because of they are coherent and their interference, there will be strong constructive interference happening there, and corresponding to that, you will get the details of that particular hmm, length, means optical length, and here actually that corresponding to that particular thickness inside the tissue. So if you are adjusting the mirror here, actually you may be mapping the layer at this region, and if you are moving the lens some more, you are maybe mapping the layer at this position. So by moving the mirror at the reference arm, actually you can map the different planes in the tissue. So this method is actually called optical coherence tomography, and here they are using the reflected light, and it is actually interfered with the light which is coming from the reference B. So the answer is actually it's using intensity of the reflected light. Now, the next question is microspectroscopy that determine the chemical composition and thermal properties at a nanoscale spatial resolution. Now, we want a spectroscopic method that can be spectroscopic, that spectroscopic method or something, and that should give the determine chemical combustion thermal properties at a nanoscale spatial resolution. Now we see that if we want the chemical combustion and other things, we may have to use a spectroscopic method. Mainly like IR spectroscopy will be good for this one. And but the problem is that IR spectroscopy cannot, because have this what they called the wavelength limit, like wavelength dependent diffraction limit. So it cannot go beyond certain spatial scale. So actually, in order to overcome that problem, we are going to use a new technique, which is called AFM IR. So how we will use this AFM-IR. So we can see what are the actually the basic modes of this AFM based imaging as well as the AFM-IR based imaging. So first we will see how a AFM based imaging is actually working. Okay, so let's start. What is actually an atomic force microscopy? So this is one of the scanning probe microscopy. Here actually what they will use the main part of the atomic force microscopy is AFM. So the main part of an atomic force microscope will be a cantilever. So cantilever is a mechanical thing which has a fixed arm and the end there will be a free arm. So it will have a particular stiffness and it can actually bend when we are applying force. So it can actually bend above or below. Depends on the force which we are imparting on the cantilever. So in the case of atom force microscopy, there will be a micron sized cantilever and the tip of the cantilever will be made in a tapered manner such that at the tip only few atoms will be residing. So just now consider that you have a specimen which have a morphology something like that. So what we will do, we will move the cantilever tips towards this specimen and either we will touch that tip with the specimen or we will go very near to the specimen. So what happens very near to the specimen, there will be some interaction between this one and what happens when it is going very near this cantilever, this tip will be get attracted by this atom due to van der Waals force and other things and cantilever start bending like this. And when there is no other things are there, it will be in the original position and it is something like some bigger thing came here, it can bend in the other side also. So and there will be one laser source. It's actually giving laser beam which will hit at the backside of the cantilever and there will be a position sensitive detector which is called. Hello, am I audible? Hello. Yeah. So I'm seeing here it is like a ESIC Faridabad library. So you are actually a student of this biophotonics course. Huh? Okay. So yeah. So here actually, whether I'm audible? Okay, okay. So here actually I'm saying about atomic force microscopy here. So you can hear that. So if you have any doubt, you can just ask. So it's actually I did a almost like a 10 questions uh, answer session now. So yeah, this is going to be like a, almost like a end of the session. Means yeah. So anyway, I'm discussing the. So these sessions are actually starting at 6 o'clock to 8 o'clock. So yeah. So next time onwards, actually, you can be come at 6 o'clock also. And anyway, I'm recording this session also, and this will be available in YouTube after some time. So yeah, now we can see the sessions here. So I am presenting. I think so. If you have any doubt, actually, you have to. If you have a mic or something, it is better because when I'm presenting, actually, I cannot see anything other than the presenting screen only. So if you want to interrupt me in between, actually, it is better to interrupt using mic or something. So next time you can actually consider that also. So in the case of a AFM cantilever, AFM atomic force microscopy, they actually use a cantilever, and the tip of the cantilever, it will be tapered and it made in such a way that then at the edge of the tip there will be only few atoms will be there, and when the cantilever is moved towards one surface or something, there will be some interactions, and based on that interactions, cantilever can bend in downside if there's interactions are attractive, and it can bend in the other side if that interactions are repulsive, or actually the cantilever is touching on the surface. So corresponding to that bending of the cantilever, there will be a laser spot, and laser spot, and the backside of the cantilever will be polished and made a reflective coating such that and there will be a laser beam which is hitting on the polished side of the backside cantilever tip, and actually it will reaching on a quadrant photodetector. And quadrant photodetector is something arranged in such a way that there will be a four photodetectors are available there, A, B, C, D. So if there is a laser beam which is actually sitting equally on the middle portion of the photodetector, and there will be some configurations like AC minus BD or A plus C minus B plus D. So the current which is actually coming as the output of the photodetector will be zero. So AC minus BD will be zero, A plus C minus B plus D will be zero. So what happens when the cantilever tips are getting deflected, this laser spot also getting deflected. So so just think that it is deflected something like this way. So if we decrease like this way, you will get some value here, because here A will be more, C will be less, B and D are some are similar. and interpreting that particular value, actually you can see the position of the laser spot, and position will be corresponding to the bending of the cantilever, and using the stiffness of the cantilever and other things, actually you can see the morphology of the specimen through which above your scan. So this is the basic idea of an AFM. Now, so this AFM will have a, the tips are like nanometer resolution tips. So actually the nanometer resolution tips can give a nanometer resolution imaging in the case of a AFM image. Now, but AFM image can actually do on the surface, or it can give the morphology or the what you call the topology of your surface and other things. It cannot actually give what are the compositions available on the surface. So it cannot give like that. So what they will do? So now we will use AFM IR. AFM plus you will add this infrared spectroscopy along with that one. So how we will achieve that? So in that case, okay, I just came to see that whether any doubt is here. Okay, now in the case of a uh, AFM based infrared spectroscopy, what these people are doing, they will be using, there will be an AFM tip, this AFM cantilever, there will be a tip, there will be like say laser source, quadrant photo detector, laser source, and there will be your samples. Here their samples may not be that much thick like, and the sample is actually kept on a prism. Sample is kept on a prism and it start illuminating from this side. So here what happens? Here there will be total internal reflection will happen, and you will move the sample along with this light. So there will be always some evanescent field here, and because of the evanescent field is actually having some reaction species here, what happened? The sample will absorb the light and it will become some bulge. When it is become bulge, there is a chance that this AFM tip is getting deflected. So, like that way, whenever the evanescence field will come here, the sample will bulge, and the AFM tip will actually detect that particular region, and it will give the corresponding signal. So, here detection is happening in the form of AFM resolution. So, you will get a nanometer range resolution in this one. So, this experiment is called AFM IR. So here the answer is actually AFM I. It will give nanoscale spatial resolution, and it can also detect the composition. How the composition can be getting detected? So if you are using a particular kind of wavelength, and we can see that wavelength will be absorbed by that particular compound at that region by seeing the AFM tips deflection, and we can check that particular space in a more resolved manner and get understanding the chemical composition of that region. And detection is happening in the case of form of a nano scale resolution. So this is actually a, you can say, this, it gives a resolution beyond our detection limit or the conventional detection limit. Okay. So how the course is happening, you can give some feedback, how how you feel the course, and how difficulty you are feeling or something. You can type the, if you have any confusion and other things, actually you can tell, or if you have clarification. Can I know what is the background of you people? You are from bio background, and okay. So how you feel this physics part, as well as whether this is difficult or it is like interesting? Okay, if you want to, whether I had to clarify something, you can just tell that. I can just say, like last week's portions, like imaging and other things. Whether, so yeah, today's presentation, actually in the starting point, actually I told something about imaging, like basic imaging techniques and other, or techniques, actually basic imaging concept and other things. Fret, you have doubt what is fret and other things. No, this is a, yeah, okay. Does energy transfer always happen? This is like not like a fret will not always happens. There will be always some fret pair. So one thing will be donor and another thing will be acceptor. So as it is shown in that thing. So I will show the things. As all biological proteins are also so close to each other. Yeah, that I'm saying. So this will not happen for all things. So actually, this is our idea to see any fret pair, or if that things, if the proteins are not a proper fret pair, we have to introduce some fret pair such that it will do something. And most of the thing which we can see that all our proteins in our specimens are not fluorescents in nature. So usually what will happen, we will actually do specifically label different proteins with the fret pair, depends on our requirement. So for example, I can say that okay, now we want to see some. So there are like different methods. So in that one, they said now there are two, like there's a cyan fluorescent protein, and there is another. I think it is a red or something. Yeah, yellow fluorescent protein. And if this is like a fret pair, so what happens in the case of cyan fluorescent protein, this will absorb some. green light or UV light. UV light. It will absorb some UV light and it will emit a cyan. So it will have some band gap, something like that way. So it will absorb some UV light and it will come here and it will emit some cyan light. So I am saying that this is emitting some cyan light, the normal thing. And there is another yellow fluorescent protein. This is my one protein. It's a particular protein. Just see. It's a particular protein. There will be another protein which have a slightly less energy gap, such that this will actually absorb cyan light to get it excited from, and it will emit a orange light. So, so I am saying that this is a one separate entity, and this is another separate entity. So what we'll do, we will do in such a way that we will let it be. This is first fluorophore and this is another fluoro. And actually the distance actually matters very near. And if the two proteins are very near, what will happen? The light emitted by this cyan fluorescent protein will be somewhere near to that, actually the absorbing excitation wavelength of your yellow fluorescent protein. So what will happen in that case? Actually this will not emit at all. This will not emit at all. So there will be a energy transfer will happen from here to here. So you will never see going to see any cyan emission. You will see only UV is getting absorbed, and you will see some yellow is actually emitted. So what is actually the indication? The indication is that these two entities are very near to each other. If this is somehow, if this they are very far, what happens? There is nothing to excite this one, so there will not be any yellow fluorescence at all. But there is no enough near, these proteins are not very near to each other, so there will not be any fret happens here. So if there is no fret happens here, what happens? This will come here and the cyan light will come out. So in your experiment, if you are seeing cyan light is coming out, it is the indicator that these fluorophores are very near. And in that experiment, if the orange light is coming out, the indication is that fluorophore is far away. Sorry, if the orange light is coming, it is the indication that fluorophore is very near. And if there is a cyan light is coming out, it is the indication that fluorophore is far away. So like that way you can actually analyze that one. And fret pair is not like a, it's a common. Actually you may have to find out which is the proper fret pair and other things. And each fret pair may not be actually, no need to be fluorescence in nature also. Sometimes this thing can be non-fluorescence. It will just absorb the light and it will not at all emit in the form of a proper radiation. So in that case, if the fret is happening, you will see a very diminished fluorescence. And if that because actually fret will always decrease the fluorescence of your donor. So if the fret is happening, there will be what you call it, there will be decrease in the fluorescence of this donor. And if fret is not happening, you can see a very strong fluorescence in the case of the donor. So Fret pairs is actually the one which you may have to see, uh, and you have to select whether it, if it's already available in your system, or you may have to tag separately if that thing is not at all available in the system. So this is like that way. You have to see what kind of things you have to get. So either it can be fret will induce some fluorescence, or fret is actually decreasing the fluorescence, depends on your application. You can select that. Okay. If you have any other doubt, you can ask. So I am winding up the session. Actually, if you have a doubt, actually you can ask that thing in our Google group also. We will find that one, and we will try to give the proper solution also. And if you have any other concerns or something, you can ask in this kind of live sessions also. So hope this class is useful for you, and these are also getting recorded, and it will be available to your YouTube channel also. So actually in that I can say that it's, so this is still here. Actually there are options like, so hopefully you are seeing here. So you can go to your course Google group, in the sense that actually you can put here. So here, so actually here you can actually ask, start discussion here. Okay. So hopefully the session is useful for you people. So I'm stopping the presentation. So we'll meet in the next week, the new week's topic, and try to solve all the assignments. And if you have any doubt, please ask in the group, or during this live sessions also you can ask, and enjoy the learning. Thank you, and bye. We'll meet the next.